So our next speaker is from Cornami. He's the CTO and the co-founder. His Paul Master has an extensive background. And as people say, you are a jack of all trades. This guy's really a master of all of them. He's got industry experience in multiple design facets, over 100 patents issued, 35 professional publications, and specialties in a variety of fields, including many core processors and digital signal processing. So it is my pleasure to introduce Paul Master, the CTO and co-founder of Cornami.
Thank you for the introduction. Thank you guys for actually attending Linley. I think you're going to like what we're going to talk about today. Think of this as a time machine. So think of it, this was 8 years ago, and somebody came out and said, machine learning's about to take over the world. So what we're going to do today is we're going to talk about the next major trend that will take over the internet and the next major trend that will take over machine learning, okay? And this talk's a little bit unusual. There's links on every slide. You can go through the same reasoning I did and make your own conclusions. But this is exciting, and I'll explain why this will happen. Recap. We have done 2 previous presentations, and unfortunately, due to the time constraints, I'm going to assume that you've actually seen the previous presentations. The links are in the slide, but I'll really summarize pretty quickly. So we're going to be talking about a post-von Neumann world, specifically post-von Neumann algorithms. And you could argue that machine learning is a post-von Neumann algorithm. We're going to talk about something called fully homomorphic encryption. And that is a monster. It breaks von Neumann, and it breaks it in all sorts of interesting ways. And we'll talk all about that. We also talked about how you can solve post-von Neumann algorithms using something known as the dynamically reconfigurable systolic array. We will flesh that out today. We also talked about the need for something known as a computational fabric, and I'm going to assume you looked at that. So we're going to talk about the Cornami architecture, the very specific architecture we've created to do this new type of post-von Neumann machine. It is a computational fabric, and we're going to talk about why that's important for the internet as a whole, as fully homomorphic encryption basically takes over the next couple of years. So we've talked about data and why the code bases are all different, but ultimately what's happening here is we collect data, we analyze data, we get value from the data, so we collect more data. So you can see the statistics, right? They're claiming 175 zettabytes. You can Google what a zettabyte is. I'm guessing that's actually an underestimate. There's too much value to the data. And with the machine learning algorithms these days, you can make money off of it. So at the end of the day, somebody once said, gravity always wins. And in this case, it's the economic justification. And that is why these post-von Neumann algorithms we're going to talk about will take over. Okay, so what are we talking about? So inherently, since you're in this track, basically, you know that the internet inherently is not secure, right? I'm not going to bore you with all of that data. We're going to talk about an interesting algorithm that solves that problem. We'll talk about that, called fully homomorphic encryption. We're going to talk about why it's a post-von Neumann algorithm and why you cannot use the traditional technologies we have to actually make this thing run in real time. And we're going to talk about how the Cornami computational fabric can actually do this problem and do it in real time. So let's talk about von Neumann, right? So von Neumann invented the modern computer, arguably end of World War II. You could argue it probably happened earlier, Colossus machine during World War II. But we know the problem with von Neumann, right? Is and you can Google all these stuff, and the links are down there, right? The memory wall. The memory is too slow. I can't get to those DRAMs fast enough. No way. The von Neumann bottleneck, right? Every processor using the caching subsystems really wants an infinite amount of data to its DRAM. Add more processors and the problem gets worse. More insidious is the multi-core programming problem, where ultimately you are trying to use a human who can keep 5 ± 2 things in his head to guarantee the totality of the state of a multi-core problem, which means it's very, very difficult to actually utilize many, many cores. The compute mismatch. So if my ALU has the operation I care about, life is good. If the operation I need is something entirely different, I'm in a very bad spot. And the security wall, basically. Whoever thought that commingling different users' data on the same machine is a good idea? And as we're finding out, that is a very, very bad idea. So these are the known limits of Binomial. A couple of years ago, somebody came up with a clever bit of kit. This is known as a roofline model. And what this does is it shows the theoretical maximum performance of a von Neumann machine. And there's a cutesy animation running on the upper side of the screen, and it is very apropos. So if my algorithm happens to have very low locality reference, meaning I have to go out to DRAM all the time, the bottleneck is the memory bandwidth and the latency. Von Neumann, by definition, says I'm grabbing stuff out of memory, putting it into the ALU, putting it back into the memory. It's like a piston engine. That's my bounding limit. If I get lucky and my locality reference is good, then the bounding limit is, again, the von Neumann bottleneck. It's pulling stuff out of the register file into the ALU, back into the register file. So and think of it as, you know, I can do a hammer. How fast I can hammer means how fast can I pull the nail out of the batch. So the bounding limits here of von Neumann are the data movements in and out of memory. So the word picture for this thing. So back in the day, piston engines ruled the air until somebody invented a jet engine, where that bottleneck of putting stuff in and out of a piston was taken away, and the world was never the same. So what we're going to be talking about is something very apropos, getting rid of this von Neumann bottleneck to allow compute and data to flow. So the architecture we came up with is unique. Our building block architecture, we call it a fractal architecture. It's a fractal core architecture. And what that means is we have a base building block that is self-similar at every level. And in fact, what you see on this picture is a block diagram of our fractal core. The fractal core itself actually breaks into 3 pieces underneath, and they all look the same block diagram. It's interconnected with an utterly unique network on chip. It implements the TruStream programming model invented by my friend, Dr. Fred Furtek. That is a talk for another time. It is utterly unique, and it breaks some of the problems with the von Neumann mode of computation. But where this gets interesting is I can self-assemble these blocks at a higher level to build constructs with similar architecture. And what that means is, for example, I can take 16 of the Cornami fractal cores, I can configure them together, and I can produce a RISC-V, specifically a 64-bit RISC-V core. And you notice this block diagram looks like the block diagram of the fractal core, and the fractal core looks like the block diagram underneath it and above it. So unlike an FPGA, there is no speed degradation in clock frequency when I do this configuration. So, you know, if I implemented a RISC-V on an FPGA, I'd be happy if it runs at a couple hundred megahertz. There is no speed degradation. So that means with this type of architecture, I can configure the silicon to put in wherever the software algorithm requires the exact type of machine that is required to do the job. So specifically, underlying the silicon that Cornami is building, and we're in the middle of a tape-out sequence 16 nanometer TSMC right now. The base building block is this fractal core. It has some interesting characteristics in addition to the self-similarity above and below. The intelligence, the silicon IQ, so to speak, what makes a processor smart is how many if statements can I do per clock cycle. Each one of our fractal cores can do 7 decisions per clock cycle. I can take these fractal cores and I can configure them So I can build myself a soft GPU with no clock frequency degradation. I can build a reconfigurable systolic array, as we discussed in the previous presentations. I can build RISC-Vs. I can use the Fractal cores as instruction set accelerators or DSP units by themselves. And I can put them in any order that I want. So I break the bounds of the fixed function silicon the way we currently build SoCs. And since it's a computational fabric, I can add more and more chips to increase the speed of the processor. So this is a trick only the DRAM guys have been able to do. If I need more memory, I buy myself another DRAM. Here, if I need a faster or bigger processor, I add more silicon together. And I'll show you some benchmarks that'll illustrate this in a couple slides. So, security problem. I'm not going to bore you. You can read faster than I can talk, but let's pick some of the really nasties that we cannot solve. So basically, are you positive on that die of 1 billion transistors, no one's added a few hundred transistors that no one's aware of, i.e. a hardware Trojan? And the answer, unfortunately, is no. On my motherboard, can you guarantee no one's added a little bit of silicon that should not belong there? Can you guarantee that the microcode hasn't been compromised, the firmware hasn't been compromised, that the compilers themselves or the synthesizers, the RTL synthesizers have not been compromised and are adding stuff that shouldn't be added there? And we know about all the operating system problems, the apps, the man-in-the-middle attacks. And specifically, can you trust that every one of your employees has not been compromised? Can you trust that every employee of the data that you send up to the cloud has not been compromised? And unfortunately, the answer is no. So this is a sorry state of affairs, but the problem gets worse. And the problem is basically that quantum computers are coming. So today, 65 qubits. IBM says by 2023, we'll be at 1,000 qubits. Google says in another 10 years, we'll be at 1 million qubits. The problem is that somewhere around 2,000 qubits, a quantum machine can break the security algorithm that we use for the internet. So it will be game over. Something has got to change. This is inevitable. So what's going to happen? And since we've been beating up on von Neumann, I figured about tossing another von Neumann quote. So it turned out about 10 years ago, a young PhD student, name is Craig Gentry. You can go read, the links are down here. You can actually read his thesis. The mathematics is head warping. He came up with something called fully homomorphic encryption. And, and to give you an idea of what this means, let's quote the US government. Fully homomorphic encryption is the holy grail of cryptography. Since when have you ever heard a government bureaucrat use these type of words? And in this case, it is justified. So we're just going to use the DARPA slides. So let me bore you to death, okay? So in the world we live in right now, I encrypt something on my laptop, and I trust, hope, it's encrypted on the way up. Doesn't really matter because the key's sitting up in the cloud anyway. I hope that it's encrypted when it's at rest. I know that it is decrypted when the calculations occur. If I'm going to run it on a CPU, at some point I'm going to decrypt the data. I hope and trust that after the data has been processed, somebody's storing it on a disk drive encrypted. I hope and trust that somebody will send it back to me encrypted. So the attack profile here is near infinite. So what FHE does, and this is mind warping, is it allows you to do computation on encrypted data. So the data is never decrypted, okay? And in fact, it's so important that this will be the next standard for the United States and hence the world. You can read this faster than I can talk. The applications are everywhere, but that first bullet talks legions. From DARPA's perspective, it enables the Department of Defense to leverage untrusted networks. Basically, the conclusion of DARPA US government is you cannot guarantee the security of a data center, of the employees, of the links, of the networks. The only way to solve this problem is to guarantee the security of the data. So why will this algorithm move into machine learning? Well, the reason is economic. So these are some headlines just clipped out of the internet. If you're Tesla, how many dollars have you put into the development of the neural network that guides that car? How easy do you think it is to steal that neural network? Conversely, let's put some dollar signs on it. The largest neural network on the planet at the moment is arguably something known as GPT-3, 175 billion parameters. It is almost passing the Turing test for certain verticals. And it costs $5 million to train it. How many times do you think they had to train this thing? And if I release this network out into the world, how soon do you think it'll take before somebody steals it? So if I can somehow protect this neural network, then I can get economic value from all my hard work. So these points are actually taken directly from this source. So what FHE applied to machine learning, they're known as privacy preserving machine learning algorithms, allow you to do is the training data is encrypted. The input data is encrypted. The output data is encrypted. The inference model is encrypted. And if you want to use the answer, you need to pay me. Basically, you need the key that is only owned by the owner of this. And again, this changes the rules entirely. Now, this is all great, but why do I call this thing a post-von-Neumann algorithm? Well, because it is nasty. So there's a couple of frameworks that everybody uses. This happens to be the TFHE library. It uses the same mathematics. There's a couple different implementations. This uses a circuit-based FHE algorithm. And what that really means is, at its heart, this particular library uses an encrypted AND gate. So in the normal world, I have two wires coming in, a wire going out. I do a couple transistors, and I can do it 1 times 1 is equal to 1, otherwise it's zeros. To do FHE, this 1-bit encrypted bit now turns into a high-order polynomial, a 500-degree order polynomial. 2 of those going in, they're actually tuples. It's worse than that. The calculation is now 3,000 complex FFTs, and I generate another 500 ordered polynomial. And again, it's a tuple. You can gather that this is immense amounts of computation, but the calculation is interesting. The table stakes for these algorithms is double precision floating point. And you're going to say, what? We haven't cared as an industry about double precision floating point for 8 to 10 years. Well, what I'm telling you is this algorithm requires double precision floating point. And because these algorithms are changing, the new generation of these algorithms, in addition to the double precision floating point, requires computation that has not been considered before. We're dealing with integer word widths of 16,000 bits, 64,000 bits, 128,000 bits.
Hi, Paul. We're starting to run a little bit late on time. Can you?
Oh, okay.
Thank you.
Yeah. So the computation basically breaks. Now, what's even worse is it's not only the computation, it's the data movement. So i9 is probably one of the fastest machines out there. Bottom is cores, left is the metric. As you toss more cores at it, the Intel part dies, and it dies a horrible death. So 8 real cores, the thing dies at 4 cores. And what that means is the amount of data that's being moved is overwhelming the memory subsystem. It's overwhelming the wires between the register file and the SIMD units. So what happens when we apply a computational fabric? And I'll skip over this. You've seen, this is from the previous presentation. So let's break ResNet 50 forever. All right. So this is a computational fabric running the ResNet 50 benchmark. And basically what this means is, how fast do you want ResNet 50 to run? And the answer is, how many fractal cores does it take to actually run it? And what is interesting here is that this number is linear. So we can go from 62 images per second to almost 250,000 images per second. And if you want faster, we add more computational fabric. This, by the way, is the fastest published numbers of any ResNet 50 benchmark. And again, I can make it go faster by adding more fractal cores. This is the power of a computational fabric. And if you take a look at my previous talk, yes, we've solved the dragon that lies within resonant 50. So what that means is FHE is the same beast. How fast do you want FHE to run? So typically industry parlance is you need about 1,000,000x speed up to make FHE run in real time. With enough fractal cores and a large enough computational fabric, you can now take this algorithm that will take over the internet, it will take over machine learning, and make it run at real-time rates. And the Intel core is down here just as an example, basically. It does not play in this space. All right, summary, and the implications here are interesting. So post-von Neumann algorithms, right? Machine learning, FHE, breaks the traditional GPUs. The operators are not what's in the silicon. The amount of data being moved basically hammers away at the very notion of a von Neumann machine. So next meta trend in the internet is FHE because security will demand it, because quantum computers will break it. But it's not going to get us using traditional silicon. x86s and GPUs will not get us there. The next meta trend, because I need to make money off of these very expensive neural networks, means the privacy preserving neural networks. And what that tells us is something interesting. We have been focusing as an industry on the neural network coprocessors, and they're all integer 8 or FP16 based machines. So the implications here is to do privacy preserving neural networks in real time. Every last one of those pieces of silicon that has been built in the last 8 years is the wrong silicon. And I hope you understand that to solve these post-von Neumann algorithms, you need a different approach. And what we're saying here is a computational fabric built out of this unique fractal architecture where cores can be combined together to build ever larger machines without speed degradation is a way of solving and moving these post-von Neumann algorithms to reality. So I apologize, this was fast and furious. The links are there. Do your own homework. I think you'll come to the same conclusion we did, that the world is about to change and it's going to change radically. So hopefully you'll go back to your day jobs and you guys will look like geniuses because you will be able to predict the future. It will be fully homomorphic encryption. It will be privacy preserving neural networks. And the world will be a better place because of this algorithm being taken to reality. Thank you.
Thank you. I mean, that was, if I had to put it in one word, that was intense.
It's just like the last two presentations. But again, the links are there. A friend of mine, John Watson, once told me basically the way to do your job, and I'm the CTO, is identifying the meta trends. And that's the word picture there is, where does the railway have to go? And you want to be in front of it. And this is a probable future. And this one is pretty good.
So we got a lot of questions starting to pile up in the question and answer. So I'm going to start trying to shoot these off.
Yeah, please.
So first one, in your 16 nanometer chip that you guys are taping out, how many fractal cores have you implemented?
Okay. Excellent question. We're not announcing the actual die chip today, but let me give you a tease. So since we can't program many cores, and that's a known problem, every time Moore's law has doubled the number of transistors, or maybe 0.25 these days, or 0.4, whatever your number you want to talk about, we've tossed those cores at the processor. So the processor core gets bigger, right? The caches get bigger. We do speculative execution, a gift that never ends up giving what you expect. Branch prediction, dot. Our viewpoint is, if you can use cores efficiently, then the real question you want to ask is, how small can I make those cores? Not how big I can make those cores. And to give you an idea of the 7 nanometer Apple part, a core is 1 billion transistors. I haven't done the math on the 5 nanometer part. It's the wrong approach, we think.
Okay. So when you quoted the 1 million speed up for silicon performing FHE,
Yes.
how many fractal cores do you guys estimate to solve that problem?
Yeah, so it depends on the application, obviously, right?
Mhm.
But I'll give you a range. 500,000 to 3 million fractal cores on the
Mhm.
FHE stuff. We've seen real-time performance. And again, where we're at is we're deep in the tape-out sequence. All the numbers you've seen in this presentation are from our ASIC emulation systems. So I'm counting clock cycles at this point.
So I know you're not discussing tape out or anything, but do you have a rough range of, can you give us anything about the power and the area or anything about these fractal cores?
Oh yeah, yeah. And again, the first presentation, basically, where does the power go in a von Neumann machine? Well, it goes into the data movements, right? And I'm not the only person talking about this. If you can eliminate the data movements, you get rid of the majority of the power dissipation. And specifically, what I'm zeroing in on that most people ignore is take a look at those register files. They're massive, especially in a GPU. The amount of power that's going in there is hellacious. And I have to do it. I go in and out of those register files because that's what a von Neumann machine does.
Mhm.
Eliminating that basically cuts the power significantly. So when we announce this chip, you'll like the power numbers. Let's put it that way.
Okay. So FHE is, I mean, like you said, there is existing solutions for FHE, but one of the concerns is the possible operations on the encrypted data seems to be limited. What is your perspective on this and the trend forward? And maybe do you have some rough ideas of some timelines maybe?
Yeah, it is. So if you go out and query the industry when FHE will become reality, the number you get back is 8 to 10 years. So that is, multiple generations of Moore's law. And the reason is you need a 1,000,000x performance on a GPU or an x86 to actually make FHE real time.
Mhm.
A computational fabric basically eliminates the bottlenecks. So it's kind of the analogy of, yeah, if you have a piston engine running a Spitfire, yeah, but we have a jet engine. The rules of the game are now entirely different. We can
Mhm.
configure the silicon to match the computational operators that are required by FHE. We can configure the silicon to match the operators in any order that's required by FHE. We can make the computational fabric as wide as the algorithm demands and as
Mhm.
deep in terms of pipelining as the algorithm demands. So different set of rules that apply, and again, to this close von Neumann FHE algorithm. You might,
So the other,
good.
oh, sorry, continue.
Oh, I was
You,
going to add, the one more thing is most people that are playing in the FHE space are doing, FHE light. They're doing addition, right? Because I can get away with really, really slow addition on GPUs and x86s. But, the world requires multiplication. Heaven forbid it requires division or a tangential function. Can't be done using conventional technology today.
Mhm. So I guess this is going to be our last question since we're about out of time. So are your fractal cores and in general also by extension FHE, will you guys support machine learning, and does FHE, can you perform machine learning on encrypted data?
Yes, absolutely. And in fact, you saw the
Mhm.
ResNet 50 numbers, machine learning numbers. I mean, we
Mhm.
know machine learning will go everywhere since we're now to the point where these algorithms, outperform most humans, right? Pattern recognition, and it's used everywhere. Applying FHE on top of that, or FHE standalone, basically, is the next generation. And for hopefully the economic reasons I outlined, it will happen because gravity always wins.
So you see it as a path forward, but not currently can you perform machine learning on
Yes, yeah,
encrypted data from?
absolutely.
Oh, okay.
You now have the fastest ResNet 50 numbers on the planet, and if somebody comes up with a faster number, I'll just increase the number of fractal cores and make it faster. It just changed the nature of machine learning.
That
Computational.
doesn't make it a fair competition anymore then.
No, it's not fair anymore at all. We broke ResNet 50, let's put it that way.
So we're about out of time, but I would like to remind everybody, since we do still have questions piling up, we have a breakout session with today's speakers in the security session, as well as from Halo Technology from the previous session. So I recommend you guys go line up, get in those breakout sessions, and try to get some of these questions answered, because I know I didn't get to all of them today. And I want to thank you, Paul, for just blowing my mind today.
Well,
Thank you
it's fun working
for
on
having me.
bleeding edge, and this is the edge. So appreciate it. Thank you.
Okay. And that concludes our session today. Thank you for having me as your moderator. And yeah, this was fun. I want to thank all our speakers for taking time out of their busy schedules to kind of discuss what they're doing, making us a little bit more knowledgeable about security, and honestly giving us a little bit more to speak about at dinner when we want to try to impress our friends. Have a good one, guys. Thank you.